All right, so hi everyone. I'm Jose Carmena. I'm going to be telling you briefly in the next 15 minutes or so a little summary where we see the invasive side of BMI. Medin and Paul have already very well described the field, the different approaches. What a little bit is where we in terms of what are the main roadblocks or challenges that prevent this technology to be deployed at the level of a like a viable solution. What are the main problems ahead of us, and then a little bit of the road ahead of new things and technologies that are emerging and we're working on too, and as well as new areas within the whole concept of BMI. Okay, so something I need to explain one at this point. The whole motivation of BMI for prosthetics has been demonstrated times in animal models and in humans. The therapeutic potential of this technology for a variety of neurological conditions, some of which are displayed in this slide, and also we also see actually the different types of approach. We can go from fully non-invasive to invasive, which are the ones I will be talking today about. Okay, so the field loaded in the last 10-15 years to the point is now it has some community, society, journals, sessions in the main conferences, workshops. Many some very well at the beginning is really basically a community of people working at all levels of this closed loop system that you see in this figure, and where the challenges all over from materials, signal processing, machine learning, controls, robotics, actuators, and of neuroscience, and then all the clinical part and regulatory aspect of it, which is actually extremely important to make something from an observation in a lab all the way to a clinically viable solution. Okay, the big word, but at least there's already a critical mass of institute laboratories, basically scientists and engineers worldwide, in which IEEE is playing a big part in doing this all the way to clinic. So what are all the challenges that remain in order to see this at the level of what will be the pacemaker for the heart or other implant devices that are basically considered a clinically viable solution today? So I have grouped them in two categories. Okay, one I was challenge one to the actual implantable technology in the brain and parts of the body. Really, all that really what you see in this figure with in this side has a pretty bulky connector attached to his head. This is the first patient of one of the ongoing trials in the US. This is the BrainGate trial, and this is the very first patient implanted, I think, back in 2005 or 2006. With the technology you see depicted in these figures, right? This is the current FDA-approved technology. It's basically very invasive. It's like a little bed of nails of about 4 by 4 millimeter, and gives you about 100 channels to the brain from the cortex. And as you can see, it's wired, and basically is not what you will think of as a fully implantable device for someone with some neurological condition. Okay, so it does a good job to allow us to basically test this hypothesis about whether this technology can help people with different conditions, but it's not in close to what we envision as something that people will be wearing. So the goal is to automatically extend the lifetime of how this technology basically works, and I'll talk about this in a moment, but also to miniaturize the technology to make it less invasive as possible, and while increasing bandwidth and decreasing power budget needed to get information from the brain out. So it's basically all about size and energy at the front end. Okay, and this is going to be limited to what we want to really put there, how many channels we want and all need to record from a given application and so on. So this is a very active area right now, and many groups are developing very impressive ASICs to basically, some of which are here, capture images from my colleagues, and they are this all come from Jan Rabai's group. And this is an example of work where you can get with very little power in the order of microwatts, send some channels and wirelessly send them basically elsewhere. It's really power communication of these channels. So actually, recent solutions that are very exciting. So in the group Autonomy, Code Brown, they published a couple of years ago. The first towards having the technology you see on the left, to have a fully wireless and in a natural way in macaques. So it's starting to get there, and this is only going to get better. So I think this not that we're not going to see these technologies miniaturized and minimum invasiveness to the point that it will be safe, basically being implanted in large numbers. However, other problems associated with this challenge, where the main related thing remains is the biophysical interface, which is basically with the problem that this technology was never invented to last in the brain for decades or the lifetime of the user. So it's technology that we adopted from the science community, and many issues, both biotic and abiotic. So in terms of why the signal gets degraded through time. And so there, about the biotic reasons, we have scar tissue formation, infection, micro due to micromotion. There's a long list, really, there of these rigid devices, or electrodes that get in the brain. But there's also a lot to blame to the actual materials that these devices are made of, and and insulation capabilities of the materials, and how long they last in the brain. And of course, the actual size of them, which is still pretty bulky, so they are in the order of dozens of microns, so 50 microns. And very exciting work in different labs right now, and in the US and worldwide, showing basically that when you get too close to a few microns in terms of with flex electrodes, the damage that causes into the brain and the longevity of the recordings increase dramatically. So a lot of hope that by extremely miniaturizing the probes and better materials, this problem is going to be solved. So this is in this image what you're seeing, what it looks today with conventional technology, off-the-shelf technology used for system neuroscience type of applications. The good side of the story, right? You get beautiful recordings. So you are seeing here extracellularly recorded in the motor cortex of a macaque monkey 3 months after implanting these electrodes. And basically, the quality of the signals is excellent, and you can keep these recordings for more months, close to a year, after which the signal is going to start decaying, and there's a variability from animal to animal in how fast these signals decay. So longer you get a few years, if you're lucky, of this recording before you only get noise. Right. So the good for neuroscience, or even for developing technologies for neuroprosthetics, hoping or while waiting that the actual ultimate interface will be built. Okay. Well, we in Berkeley, with Michelle Maharvitz and other colleagues in the department, an approach that we call a neural dust. So this vision of how we could solve some of these problems associated with the longevity of these recordings that is short at the moment, and also and the reasons why this happens. Basically, tether, wired, rigid type of devices. So coming with is an idea that basically consists of having tiny microscopic size little modes of passive cells. So these are made of materials. It's a crystal that has a little circuit and a tiny sensor. In this case, the sensor is basically the differential recording, right? So two electrodes are going to be sampling in the extracellular space. The idea is that these modes are interrogated with ultrasound from somewhere in the intracranial space, for example, and by making so the ultrasound basically energizes these modes and makes them resonate. And what happens then is that the little mode becomes like a little power generator that by the circuit, this simple ASIC that is attached to the mode, and then that allows to sense what is in the vicinity. So you can see, let me actually, yeah. So this how it looks. I'll get to this in a moment. How it looks in the periphery. Let me tell you a little bit more about actually how that works. So as I mentioned, you have this interrogator that's a carrier that is on the frequency going to make this piezo crystal to resonate, and that's going to power this little circuit that is going to be able to record from whatever is. Let's say there is a neuron nearby, and this charges. So there is the action potential that is being recorded by that little circuit is actually going to change the impedance of that circuit, meaning because the piece is attached to the circuit, right? So the vibration pattern of that little crystal is going to change, and it's going to be encoded the backscatter going back to the interrogator. So in other ways, we have a scattering system that allows us to power and communicate with ultrasound. We send pulse of ultrasound, we put a little sensor with information back in the echo that basically includes some aspect of the amplitude and power of that sensed element, in this case a neuron. Okay, work that is, I mentioned is in collaboration with Mitch Harvis and other colleagues, the two heroes that did all the work of the first vivo demonstration are DJ Liu, now works for Neuralink, and Ryan Neely, that is just graduating from my lab, finished experience a few years ago. What you hear in this figure, bottom right, is how actually dust looks today. So it's the size of more of a meter. So we're using it for peripheral type of applications, which is a very hot area also, both for peripheral neural prosthetics and also a more recent area known as bioelectronic medicine or electroceuticals. So at this moment, Neurals allows us only to record, but we are working with Rick Mueller also in the ES department, Berkeley. They're developing an ASIC for stimulation. So they used to have this closed loop modulation system, same type of technology. How it looks, just give you a little bit more details in the actual sciatic nerve of a rat. This is a demonstration that we published last summer. As you see in the image, basically it's a little circuit that is set here in this mode. For the first type of demonstration, it's just one FET transistor, 2 resistors, and that basically allows us with electrodes, one at the gate of the FET and one from ground, allows us really to change the impedance of the circuit, which is going to change by definition the mechanical impedance or the vibration of this piezo, and the echo going back is going to have that information encoded there, as I mentioned before. Really, how the data looks like. Here you see in the top left, in the sciatic nerve, what we call the ground truth. So you put an electrode reference to ground, and you change the electrical stimulation downstream. You get different action potentials, and the more stimulation that you apply, the larger the action potential. So this is really what you get with conventional technology. And here, right, you see what you get doing the same experiment with the neural dust mode. And here, the difference between the two, which you can see the fidelity, and also in the bottom curve, you see that basically the peak to voltage of the signal being recorded increases to increase the stimulation intensity.